Thank you everyone for coming back. Like I said, it's Friday, so that's exciting. Rochester, I hear, has moved into phase 2 of reopening, so maybe we're inching our way back to some kind of return to campus potentially, hopefully for the fall. We've been talking in this class about linear interpolation. This idea that sometimes we're going to need to find information like the specific internal energy, or little u, of a material at a particular state, and that information might not be directly on a table, in which case we will assume that the function, specific energy as a function of temperature, we'll assume that that's linear with temperature between the two rows we're looking at on the table. We know it's not true, but the easiest way to deal with nonlinear problems is to try to get lots of data points that are close together and then assume that it's linear between your data points. So to do that, I'm going to argue that all the time we should determine this interpolation factor A, which is going to be the known variable. If in this case, if it was temperature, we'll take the temperature we want minus the minimum temperature on the table, divided by the range of temperature between the rows on my table, and that will give me this factor A, which will range between 0 and 1. So if I've gone 25% of my range in temperature, that means I must also have gone 25% in the range of my specific internal energy on the table, because that's linear as well. So then this equation is also true. So if I can find the interpolation factor from the temperatures, then I can use it to find my specific internal energy. So the title of the lecture today is Thermodynamic Properties of a Pure Substance. But when we talk about linear interpolation, it's kind of like stuck in the middle with you, right? It's not even I'm old enough to have been around when this song came out, but it's a good song. Right? So we've been talking about conservation of energy using the first law of thermodynamics, right? And we've been looking at closed systems. So this is not actually the base level of the equation. To get to this point, we've already assumed that the change in energy is dominated by the change in internal energy, so that changes in things like kinetic, potential, and spring energy can be neglected. But if we make that assumption, then our equation looks like this, where we have the change in the internal energy is equal to Q minus W. We learned how to find W. That's the integral of P dV. And now we have an equation for the change in internal energy. We look for the intensive version of that property, which is little m times delta U. But then that delta little u we don't know how to get, right? But if we did, we could use it to get Q. So last class, I told you that we could find the specific internal energy by looking it up on tables. And that's what we're going to do today, is some examples. Right? So we said, okay, how do I find specific internal energy? I know I have some material in my system. Let's say it's water, right? So the water could be liquid water. So this is our vapor dome. So if we're to the left of the vapor dome and above the vapor dome, then we have liquid water, and I can find that on table A5. Now, if we're above the vapor dome, but to the right of the critical point, that's the apex on this vapor dome, then we have steam, or superheated vapor. And I can find that information on table A4. Now, I may be in the case where there's some phase change happening. So I have some liquid water and some vapor, right? So both of those two phases exist at whatever saturation temperature is associated with whatever pressure the material is at. So it's some combination of water and water vapor at that particular saturation point. And if I know the quality, or if I can figure out the quality, then I can determine all the properties that I want using table A2 or A3. So if I'm talking about water, the tables that I want to use run between A2 and A4. The difference between A2 and A3, I believe on A2, you have round numbers for temperatures. So you'll typically use A2 when you have a temperature as one of your pieces of information. And you'll use A3, which has round numbers for pressure on the left-hand column. You'll use A3 when you have pressure as one of your two independent intensive properties that you need to fix your state. So let's say we've got a single phase substance. We can either look on table A5 or A4. So here's an example. We're looking for the properties associated with superheated water, that's another way of saying steam, at 10 megapascals and 400 degrees Celsius. So we actually did this last time. So I look on table A4, and A4 is a series of different tables. So first, I look for the table that has the right pressure on it. So this table has 100 bars of pressure, which is equal to 10 megapascals. Now, the other intensive property that I have is temperature. So the temperature is 400, and I'm fortunate in this case because that temperature, 400, is a row on my table, so I can just read the numbers off. If I want the specific internal energy, that's little u, but I can also find specific volume, which is, remember, 1 over density, specific enthalpy, which is little h, and specific entropy, which is little s. So I can look all those things up directly because I have 400 degrees as a row on my table. But then we said sometimes we're going to have to do linear interpolation when we don't have, in this case, let's say we knew the pressure, but the temperature wasn't a row on the table. Then we need to do linear interpolation. Like I said, we can find the interpolation factor by using the property we know, for example, temperature. And then we can use this interpolation factor to find the property we don't know, for example, specific internal energy. So here's an example. So let's say we're trying to use linear interpolation and we want to find the specific internal energy. We want to do this for a case where the pressure is 1 bar, which is right about 1 atmosphere, and a temperature of 410 degrees. So here, I'm still going to look on table A4. I look at the top of all these subtables, and I see one table that has a pressure where my pressure is 0.7 bar. So I know that's not the right table. But then I have another table where my pressure is 1 bar, and that is the pressure that I'm looking for. So I know my answer is going to be somewhere on this table here. Now, I also want to find the temperature of 410 degrees. So the way these tables are set up, it's kind of efficiently done so that they're side by side here. So the temperatures that are on this leftmost row here run right across into this other table. So here I'm trying to find a temperature of 410 degrees. Unfortunately, 410 degrees is not a row on my table. I have 400 degrees and I have 440 degrees. So I know I'm going to be somewhere in between those two temperatures. So again, I find my subtable that has the pressure that I'm looking for. I know I'm looking for specific internal energy, which here is kind of circled in purple. And then I know I'm somewhere between 400 degrees and 440 degrees, which means my specific internal energy is somewhere between this minimum value, 2,967.9 kilojoules per kilogram, and this maximum value, 3,032.6 kilojoules per kilogram. So I know I'm somewhere in between these numbers. So I want to find my interpolation factor A. So here, I know A is my actual temperature minus T min divided by T max divided by T min. So here, and then if I know A, I can find U, right? And then here I can take this equation and rearrange it a little bit to isolate for the specific internal energy at the particular temperature that I want, right? So these are the equations that I want to use, right? I don't know A, but I do know T actual, that's 410. T min is 400. T max is 440. And T min is 400. So I can find A, right? And then in this equation, I don't know A and I don't know U at the temperature that I'm interested in. But if I use this equation to find A, then I can put it in here and find UT using this equation here. So it's a system of two equations, right? So in this case, A, probably you could do this in your head, right? So this is 410 minus 400, that gives me 10. divided by 440 minus 400. That gives me 40. So 10 over 40 is 1 over 4, which is 0.25. So I'm a quarter of the way between these two values. Now I can use my equation that U of the temperature that I'm interested in is going to be U min, 2968 about, multiplied by A, which is 0.25, multiplied by the difference between these two numbers. And if I put that information into my calculator correctly, I get that the answer is 2,984.1 kilojoules per kilogram. Does that make sense? Does anybody have any questions about this? I know it sort of seems like it should be simple, but there are certainly, simple doesn't mean easy, right? So there are certainly times in class where people will kind of, try to do this quickly and get it wrong. So does anybody have questions about this idea of linear interpolation here? All right, I will keep moving on here, right? So now we have a bit of a trickier or more complicated problem because our second example, it asks us to find what the specific internal energy is at 0.8 bar and 220 degrees Celsius, right? So here I'm in a bit of a bind because I don't know the pressure, right? So here I have a table for pressure at 0.7 and a table for pressure at 1, both of those units in bar, but I don't have any information in between there. So I don't have the right table for the pressure I'm interested in. And if I look on here, I also don't have the right row for the temperature. So this is what we call double interpolation, because to find the right answer, we're going to have to interpolate with pressure and we're going to have to interpolate with temperature. So it's almost like I have to make a little part of a new table that's in between this table for 0.7 bar and this table for 0.1 bar. So I'll kind of duplicate these two rows at 204 and 240, and then I'll interpolate in between those 2 points using the temperature that I know. Right? So here the pressure that we want isn't one of the pressures we see on the table, but we know it will be somewhere in between here. We want to find the specific internal energy. And we know our temperatures are somewhere between 200 and 240. So I kind of have these 4 points, and I know, if they're sort of the 4 points on my table, I know I'm somewhere in between the bounds set by those 4 numbers. So if this was at 1 bar, I'd have some number in between these two values. If we were at 0.7, I'd be somewhere in between those two values. And then I'm somewhere in between whatever interpolated value I'd have in there because I'm somewhere in between those two pressures that are on these tables. Right, and this can be a little bit difficult to describe in words, right? So sometimes I like to draw graphs because it helps me. So here, it's like I have 2 linear lines, right? So one line is at my lower pressure, which is 0.7 bar. And one line is at my higher pressure, which is 1 bar. So these 4 points represent the 4 data points for specific internal energy that I know, the ones that are on that table. So now when I'm doing double interpolation, I have 2 options, right? So sometimes I'll know the temperature, right? So my temperature is in between T min and T max, and I'll know the pressure, which is in between P1 and P2. So my double interpolation means I can interpolate with temperature first, or I can interpolate with pressure first, right? So my first option would be to interpolate with temperature first. So here I would find what my interpolation factor A is, where A is defined by my temperature range, by my known temperature and my temperature range, right? Just as we've defined A before. So if I do this interpolation first, the first interpolation you do, whether it's temperature or pressure, you'll have to do twice, because you'll have to find the new point at the low pressure and the new point at the high pressure. If we were thinking about this in terms of the tables, we're basically making a row on both of those tables that's at, in this case, 220 degrees. And then once we have these 2 points, then we'll find a new interpolation factor, B, which is related to these 2 pressures. It's going to be the same equation, but now we're going to have a known pressure minus P min divided by this range of pressures, P max minus P min. And then we'll interpolate with B, but we only have to interpolate with B once. So my advice to you is going to be, look for the interpolation that's easier and do it first. In this case, you may have noticed, and you may not have, that's okay too, but you may have noticed that A is going to be 0.5. If I have to interpolate, 0.5 is kind of the number that I'm pulling for, because that means I can take the average of my two numbers, right? If I'm linearly interpolating, if I have a linear function between 2 points, 0.5, that's half the way there. So that means it's going to be half the distance, and half the distance is described by the average, right? So I could just do the average of the two numbers. So here I'm doing this average 2 times, and then I only have to do this other interpolation once, right? So here, if I was drawing a table out, I would have 4 values that I know from the table, right? And then here I would use, ultimately I want to get, it's a bit like tic-tac-toe, or maybe you're too old. I don't know if they have this game show anymore, but it's called Hollywood Squares. It used to be hosted by Whoopi Goldberg, who, I don't know, again, I'm probably dating myself. You might not even know who she is. But you're trying to get to that center square. That's the answer that we want, right? So if we interpolate first with temperature, what we would do is we would use A to get to this point here, interpolating between these two known values. Then we'd use A again to interpolate between these two known values. And then once I had those two values that I've interpolated because of the temperature, then I would interpolate between those two using my interpolation factor B. My other option would be to interpolate first with pressure. Now this is almost the same, but if we interpolate with pressure first, then I have to use my interpolation factor B, which is related to pressure, twice. So I would interpolate with respect to pressure once at the low pressure and once at the high pressure. And then I would use my interpolation factor A to interpolate between these two known, or these two new values of specific internal energy at this intermediate pressure that we have. So when we double interpolate, it's really a bit of an understatement because we're interpolating 3 times, but we're only interpolating with 2 different properties. So we're interpolating with temperature and then we're interpolating with pressure. The one you pick first, you'll have to do twice. So look for, if for example, one of your interpolation factors is 0.5, do that one twice because it's a little bit easier. So again, I could set up this table, and if my pressure that I want is this column in between, what I've done here, again, we want to get to the center square. So we're looking to interpolate first with pressure. So we're now trying to find that middle square on the top row. And then again, we use the interpolation factor B to find the middle square on the bottom row. And then I would interpolate with temperature between those two values. So hopefully, seeing it in the table, seeing it on the graph, hopefully that kind of helps conceptually, helps you understand what we're doing here. But now here's our example, right? So we know that we're trying to find some intermediate pressure between these two graphs, and we have to find some intermediate temperature between 200 and 240 on both of these curves, or both of these tables, I'm sorry. So I know my interpolation factor A is 0.5 because 220 is half the distance here. So 220 minus 200, that's 20. 240 minus 200 is 40. 20 over 40 is 2 over 4, which is 1/2. And my interpolation factor B is going to be 0.8 minus 0.7, that's 0.1, divided by 1 minus 0.7, that's 0.3. So I'm going to have 1/3 there, right? So here I use interpolation factor A, and I can get a value. I interpolate again here, and then I interpolate with B 1/3 to get another value, right? So here, it maybe makes a little bit less sense. So I made this slide as well, which is showing how we would do a double interpolation. So what I'm going to say is when you're doing a double interpolation, try to make your own little table like this. So it's going to be this 3x4 matrix, right? So here you're going to have the temperatures, the two known temperatures on the table and the one in between, your two known pressures and one in between, right? And then whatever property, in this case, specific internal energy. So now I picked 2659. I put that up here, right? That's my low temperature value, specific internal energy at my low pressure, right? I take 2719, that goes in the corner here. 2658 goes up here. And 2718 goes here. My advice is going to be do the easy interpolation twice. And here the easy interpolation, in my opinion, is interpolating with temperature because we're halfway in between, or we can take the average. So I'm going to use interpolation factor A twice. So A is 0.5. So first I'm going to use it at the low pressure. So I'm going to try to fill this in with an actual number. So I look at these two numbers here. I take the average, and I get that this is 2689.2. I put that on my table. I do the same thing at this higher pressure. I'm going to use A again. Halfway in between these two numbers is 2688.3. Now, you might get to maybe a multiple choice question on a test or on a quiz, and you might notice that there's not a lot of difference between 2688.3 and 2689.2. So maybe you wouldn't even use a calculator in here, and you would just look for any kind of number that's in between these two values. But if not, then you would do the interpolation. You would use interpolation factor B, so 1/3 of the difference. Notice here that U is actually moving down from 2689.2 to 2688.3. So when I say U min, when we're defining B, it's really U at the minimum temperature. So it's U of T min, right? So here, I then 1/3 of the way between these two is 2688.9. So if I look at these, I'm closer to this value because the pressure that I want is 0.8 bar, right? Which is closer to 0.7 bar. So this makes sense that I'm closer to that number than to this number over here. So that's double interpolation. It's kind of a cumbersome process. It's a little bit tricky because there's not really much in the arithmetic that's difficult here, but it's just that there's a whole bunch of arithmetic to do. So it can get a little bit awkward or cumbersome, right? So I think if you just take your time, then you'll tend to do this correctly. Right? So we did this example for temperature, where we had temperatures and pressures, and we were trying to find specific internal energies. But we could use the same process if we were trying to find specific volume, or if we were trying to find specific enthalpy, or if we were trying to find specific entropy, or if we were given the specific entropy and the pressure, we could use that to find the temperature as well. So you can basically use this strategy, this process, for any different property. I see that Matt McDermott has his hand up. Matt, what's your question?
Yeah, can you repeat real quick how you found B?
How I found B? Sure. So let's go back. Thank you for the question. Right? So here, our pressure that we're looking for is 0.8 bar. Right? I'm interpolating between 0.7 bar and 1 bar. So I'm going to find B as P that I'm interested in minus P min. Right? So that's my numerator. That's 0.1. But my ranging pressures is going to be 1 minus 0.7. Right? That's 0.3. So here I have 0.1 divided by 0.3, which is the same as 1/3, which is 1/3 or 0.33. Does that make sense?
Okay, that makes sense.
Okay, thank you. It's a good question. And it's, if you have a question, it's much better to get the answer now than to wait till you're, in the middle of the homework or in the middle of an exam. So I do appreciate the questions. Thank you. So let's get to where we were, right? So we can use this for all kinds of different properties. Right, so thank you for also lowering your hand. I know that when I'm in these meetings, sometimes it's hard to figure out how to do that. So if you're looking to lower your hand, I think you just press the same button that you used to raise your hand. But I'm only about 90% sure on that. So,
Yep, that's right.
Excellent, thank you, Matt. So that's what we do when we're trying to find a superheated vapor or a subcooled liquid. And those different states or phases are better or maybe a little easier because remember, temperature and pressure are independent in that case. Sorry about the audio quality. I do have a better, so right now I'm over Wi-Fi, so I bought a power line adapter. I'm hoping that improves the audio quality and the internet connection to my computer that's here. So hopefully that's supposed to come today from Amazon. So I hope that makes things a little bit better. So we're going to try to find out how to interpolate for things that are under the vapor dome where temperature and pressure are no longer independent, where they're dependent properties. So remember, we talked about this idea of quality, where quality is the mass fraction of the vapor. So you take kind of the mass of the vapor divided by the total mass. So it's kind of what percentage of your mixture of saturated liquid and saturated vapor is vapor. So here, anytime we have a property that's related to quality, we will use this equation, right? So Z is just a stand-in for any type of property that we're interested in. So this is always, you notice this equation looks the same. The reason I like to do interpolation with these interpolation factors is because that's really all quality is. It's an interpolation factor. So our equation ends up looking the same. So if I'm trying to find some property as a function of quality, I take that property of the saturated liquid plus quality times the difference between that property at saturated vapor minus saturated liquid. In some special cases, in particular enthalpy on the table, so little h, they have this property HFG. HFG is just Hg minus Hf. So they did the subtraction for you. So you can put it in here and we get this value here. So we get that equation. So it's the same equation. It's just they're sort of trying to save you one step here to help you put less things in your calculator. And if you're like me, I'm really good at entering numbers incorrectly in my calculator. So maybe this saves us one mistake. So here we know we have these properties with the subscript F, which means the saturated liquid value. And we have the same properties with the subscript G, which is the saturated vapor value. And we can use this table to try to find our properties when we have a two-phase mixture. So here, this, I believe, is table A3 because it's got pressure all the way over here on the left. And the pressures are round numbers. So here, what this tells me is if my pressure is 0.04 bar, then water would boil at this temperature, almost 29 degrees. Right? Whereas if my pressure is 1 bar, which is just about an atmosphere, then my water boils pretty close to 100 degrees. Right? So here, I want to find what's the specific internal energy if the pressure is 0.8 bar and the quality is 0.9. So here I know I'm looking for specific internal energy. It's got to be between the specific, the saturated liquid value and the saturated vapor value. And we know that this is at 0.8 bar. So we're going to be between 391.5 and 2,498, right? Notice the difference here between the energy per unit mass, right? So in order to boil water, even when it's at the right temperature, to get steam, you have to put in a lot of energy to turn it into vapor. So we know we're going to be somewhere in between that 391 and almost 2500. Right? And because my quality is 0.9, right? That means 90% of my mixture is saturated vapor. So I must be closer to the saturated vapor than I am to the saturated liquid. So here I want to interpolate with respect to quality. And the cool thing about this is I don't have to figure out my interpolation factor. Because my interpolation factor, I was just trying to find what fraction of the temperature we were looking at. But here, x is already a number between 0 and 1. So I don't have to find that. I just use whatever value of x I have. So then I would go and use x to find the specific internal energy. So x is defined as the mass of the vapor divided by the total mass. X would also be this equation, right, which we get from our interpolation factor equation. So here, if I want my specific internal energy at a particular quality, then I have UF plus X times UG minus UF. And this will be the same equation if I'm looking up little u or little v or little h or little s. It's always the same. So here in this case, now I know my pressure, so I know the right values. I know UF and I know UG. I know X. So I can put all that information into my equation and find that my specific internal energy here is 2,288.1. I look at these two numbers and I say, does that make sense? And I think it looks okay because I know my quality is 0.9. So 90% of my mixture is vapor. So I should have a number that's much closer to 2,500 than it is to 390. And I think that's what I ended up with. So that's good. Hopefully, I have some confidence in this number because it looks like it's in the right ballpark. So here's another linear interpolation. This is using table A2. Table A2 has round temperatures here on the left, right? So here I can see if I had a temperature of 90 degrees, then water would be boiling if water's boiling at that temperature, then I know my pressure must be just about 0.7 bar. So here if I have a round temperature, I go to this table. Again, I know my number is between UF and UG for my temperature of 100 degrees. But here my quality is 0.25. So that means only 25% of my mixture is vapor. So more of it is liquid. So I would expect a number here that's closer to about 420 than it is to about 2,500. So let's see what we get. Again, we're going to assume it's linear between our 2 points, UF and UG. We know a value of x, in this case 0.25. And graphically, we would draw up to the line and then over to see where ux is. We're going to use the same equation that we used before. It's just now we have different inputs for the arguments. So in this case, when quality is 0.25, then I'm only a quarter of the distance. I've only moved a quarter of the distance between these two numbers. So I got an answer of 940.8. Right? So again, if this distance, if the difference here is about, let's say it's about 2,000, right? Then a quarter of 2,000 is 500. So if I added 500 to 420, that's about what I got. So I can see it kind of makes sense. I've got some pretty good confidence in that number. So this one is a little bit trickier, right? Because here we're told the temperature, but we're not told the quality directly. Instead, we're told a specific volume. So here we're trying to find the specific internal energy, and we know that it has to be between UF and UG, provided that we're at 100 degrees, but instead we're told the value of the specific volume. So the first thing that I would do here is, remember, we got to see, are we even a two-phase mixture? So I got to see, is my value of 0.9 between UF and UG? And if I look real quick, I might think it's not between those two numbers. But I have to remember that this number, to fit on the table without so many decimal points, they've already multiplied it by 1,000. So I have to take this 1.04 and divide by 1,000. So this is like 1 over 1,000 basically, which is even almost 0, right? So my number is between 1 over 1,000 and 1.673. So I know that I'm somewhere in between those numbers, which tells me that I have to have a two-phase mixture. But I don't have the quality yet, right? But if I knew the quality, so if I can get the quality from the specific volume, then I can use that quality to find the specific internal energy. So here I'm going to try to find quality in the same way that I've been going the opposite way, right? So I know X is the mass of the vapor divided by the total mass, right? I know that X is also V of whatever that quality is minus VF divided by VG minus VF, because all these properties vary linearly with the quality, because it's really just, quality is just giving us the weight for the weighted average, because I have some combination of saturated liquid and saturated vapor. So here I can use this equation because I know Vx, Vf, Vg, and Vf. So I can use this equation to find X. And then I can use a similar equation to find, or I could rearrange this equation to find X, right? But that's what I've already done up here, right? So I can then rearrange it, and if I didn't know specific volume, I could use it, and I knew quality, then I could use quality to find the specific volume. But for this particular example, it's quality that we don't know, so we're going to keep the equation in this form. So in this case, my quality is the specific volume at the particular temperature that I'm interested in, right? And the quality that I'm interested in. It's going to be minus the specific volume of the saturated liquid divided by the difference between the specific volumes of the saturated vapor and the saturated liquid. So in this case, I'm just about halfway in between, right? So here, if I thought about this as 0, right, then halfway between this would be like 0.8 something. So I'm a little over halfway because this number is very small. So I feel reasonably confident about my answer for quality here. Now I'm going to use the equation here to find Ux. So my equation here is going to be Ux is equal to UF plus X times UG minus UF. And when I do that, I see that my answer is 1,462 or 63. Right? So again, I'm about 1,000 units in between here. So here, there's about 2,000 kilojoules per kilogram in between these two numbers, right? I'm about 1,000 in between. That's about halfway. So again, I feel reasonably confident with that number. So that's the end of the interpolation examples that I have for you. I know we have a little bit of time left. You're certainly free to leave if you like, but I'm happy to kind of answer questions about interpolation if you have them.
Is there a resource available where there's just a bunch of I guess, practice problems for these? Because this doesn't seem hard particularly. It just seems like something you kind of need to do a lot to really understand.
Yeah, so I think that that's what we're trying to provide in the textbook problems. Mm-hmm. So I guess there is a resource, the textbook, if you have it, but we have assigned some homework problems as well. So you could always just look at the tables and kind of make up your own problems. But I think, we tried to assign some, a range of textbook problems so you see different variations of this. Like here, this last example we did where we tried to find specific volume, where we were given the specific volume and had to find the quality. So it's a different wrinkle. But if you look through, I think we tried to select the homework problem so that you see the different wrinkles that you might need to see. I also think you're right that this is not, it's not particularly difficult, but it's almost like, that's what makes it a trap a little bit, right? Because it feels like it should be easy, you know? So, you know, it is possible to get these wrong, but hopefully, like you said, if you practice a little bit and you take your time, you'll do fine. And this is, even though I've sort of said that this is kind of my favorite class to teach, the beginning is a little bit rough, right? Because it's not super exciting to learn how to look numbers up in a table, but we do get to do exciting stuff with them. So hopefully once we get kind of the mechanical part out of the way here, where we're just sort of going through the arithmetic, you know, hopefully we'll do some more fun stuff. Are there any other questions? All right. Thank you very much.